so today we're talking about normal distribution. So a normal distribution is when we have symmetric data. So it's another way to say symmetric. So we see that bell shape, okay? So that histogram that has a bell shape. And because we're talking about this normal distribution or a symmetric data, it means we can use the mean, and we will be using the mean now. And what we'll also be using is the standard deviation. And what the standard deviation is, it tells us we can work out bits about the data around the mean using standard deviation. So that's why we need that. All right, so when you get told these questions that we're going to do, they're always going to tell you this. So as soon as you see that it's normal distribution, they'll say it in the blurb or approximately symmetric and things like that. You know you'll be using this next bit of theory. So the next bit of theory is this 68, 95, 99.7 rule. So what this rule is, it tells us that if we have this, we've got this symmetric data, and we know that down the middle would be this middle value, this is where we would see the mean, okay? So the data's symmetric, so whatever the average is, it would be here along the scales. Now, so it would be an actual number. If we go up, so if to the mean we add 1 standard deviation, so that means we've got the mean value and we've added 1 standard deviation value to it. If we go up 1 standard deviation, or if we go down 1 standard deviation, what we have within there, so we normally say plus or minus 1 standard deviation is 68% of the data. Okay, so this is all the time. This is the case if the data has this bell shape. So you know if you go plus or minus 1 standard deviation, that 68% of the data sits between these two values, whatever they are in the scenario. Okay, if then we have also the next scenario, if we have, if we go add 2 standard deviations to the mean. So if I plus 2 standard deviations to this mean value, or if I minus 2 standard deviations to this mean value, within those two, between plus or minus 2, we have 95% of the data. Okay, and then the last one is if we go plus or minus 3 standard deviations onto the mean, we would have 99.7%. So in here is 99.7%. So 99.7% is nearly 100, isn't it? If you rounded that, that's nearly all the data is plus or minus 3 standard deviations. So this is where we can also say, if we are, and you might want to take note, if we are estimating the standard deviation, so I'm just going to call it standard deviation, SX. If we're estimating standard deviation on symmetric data, and they will only ever ask you to estimate it if it's symmetric, you can estimate it by going the range divided by 6. And why divide by 6? Because you can actually see, can you see that there's 1, 2, 3, 4, 5. Can you see there's like 6 sections there if you're plus or minus 3? And if I'm saying that it's roughly 100%, that's why we're saying that. Okay, so if ever you're asked to estimate the standard deviation from the data, just do the range, remembering that the range is the maximum value minus the minimum. So you would just take whatever the maximum was mentioned and whatever the minimum was mentioned. So let's go over this 68.95. So how are we going to work it? So let's go through a few scenarios. So if we have the mean here, and see here, we've done the mean plus 1 standard deviation and the mean minus 1 standard deviation. So we said before, yeah, that would give us 68% in the middle. Now, if you think about it, if you did 100 minus 68, you'd be left with 32% left over. Is that true? Now, you've still got these little tails here. So if you divided that by 2, you get 16%. So we can say these little tails are 16% of the data. So what I can say here, if you are, so you might write, if you are plus 1 standard deviation above the mean, you are in the top 16%, yeah? Because there's only 16% above you, yeah? And so we can do different breakups as well. So, and you sort of, and they'll play around with it. So if you think about it, if you're in the top, if this is 16% that way, that way, then all the way below it would be 100 minus 16. So there's 94% below. Is that true? Do you get that? Yeah. So you go the top 16% and maybe just write that 94% below. Even 84 below. Beg your pardon. 84 below. Okay, so there's little numbers that will come up. All right, so we're just showing you now, they can play around with the numbers a lot. So say here, this is 1, this is 2 standard deviations, and this is 3, and then this is minus 1, minus 2, minus 3. So sometimes they play around with it with the question, and they say they might have you sitting here, like minus 2, but then they might only have you sitting at 1 standard deviation. So then they might say how much percent is between here. And this is where you can use all these little break it up there. So you could say it would be all those little sections. So you could say it was 13.5 plus 34 plus 34. Okay, so that would be, what would that be? 70. what did I say? No, it'd be 81. Yeah? 0.5% is in between there. Okay, so you're going to see that in a few questions, but you've got these in your reference book, so you can use it and you can always refer back and count up which sections you've got. All right, so let's go through. Let's practice the 2 here and have a look at the 2. So we've got the mean, and if we're plus or minus 2, we saw before we've got 95. So 95% of the data lies between that value and that value, whatever it is, if it's symmetric. So then if you think about 100 minus 95, we're left with 5%. And then if we break that up into 2, so we see these little tails here are 2.5%. Okay, so that's where we're saying that. And you can see, so if you were plus or minus 2, so say we're here and up here, so you can always add up and it depends. So if you add all those percentages up, you get 95, okay? And if you add these 2, you'll see that adds to 2.5. All right, so as I said, you've got this in your reference book. You can refer to it. And the last one, so plus or minus 3. As I said, they're very, very tiny little tails, because if you look, when you've done 3, you've got 99.7. So if you do 100 minus 99.7, you're left with 0.3%. So very little, under 1%. So these tiny little pockets become 0.15% each. Okay, so if you had if you were up here, the value's there, you're in the top 0.15%. Okay, so this is what the and then there underneath we could do it. So you'd be down here if we go minus 3 and plus 3, all these values add up to 99.7, and you can see the little pocket there is 0.15. Okay, and then just to go over, if you're at the mean, so remember it's symmetric data, so 50% is above you or above it and 50% is below it. So that's just, and that's when you only when you have symmetric data, and that's why we're using it. Go. So the lizards in a reptile house are given cricket nymphs to eat at feeding time. The lengths of the cricket nymphs are approximately normally distributed. So can you see there, they've told you, and remember I told you in the blurb they have to tell you that it's this case. And as soon as you see that, that's when you should know. I often, when I doing questions, as soon as I see that, I draw my little bell shape near my page because I know they're going to start talking about it. So here, and then it says with a mean of 12.7, so there it goes. So I'll chuck that in there. There's 12.7, and it says a standard deviation of 2.3. So that's if I went up one standard deviation. So that means I do 12.7, add 2.3, I get 15, don't I? Yeah? So at one standard deviation above, you're actually at 15. And if I did two standard deviations above, I'd be at 17.3. I'm adding another 2.3. Is this making sense? And then if I do another 3, add another 2.3. So what would that be? 19.6. You all happy with that? Yeah? And then you can go backwards. So you do 12.7 minus 2.3. So that'd be 10.4. And if I minus another one, it would be, what would that be, 7.9? Is that right? Sorry, getting brave. And the last one would be 5.6, yeah? If you went minus 3, is that right? No, that's not right, is it? Oh, it is. Okay, so that's me just drawing them all out. You don't have to draw them all out, but I'm just showing you because this is we're learning it. Okay, so they've been nice here, and they're even telling you you're using the 68, 95, 99.7 rule. They don't need to tell you that in the exam once they've told you this. Yeah? So that they're just being nice. So it says determine the percentage. These are very important words to highlight because they will use different things. So determine the percentage of cricket nymphs expected to be longer than 15 millimeters. So if we go up here and we have a look, 15 is on my one standard deviation. So if I just draw that, and they want a longer. So if 15 was here at one standard deviation, remember if I drew up there, what was this little pocket on the one when you were one standard deviation? Remember there was 68 in the middle. What were the little pockets on either side? They were 16%. So how much were longer? That means they were that way. So we just say the percentage was 16%. Okay, so yeah, sorry, up here my math was not good. So this one should be 8.1 and 5.8. Okay, let's look. The percentage of cricket, I'm doing 2. The percentage of cricket nymphs that have a length between, so the cricket nymphs, the percentage between 8.1 and 15. So up here, sorry, this is our corrected one. It was here. So if you look at it, if we had the standard deviation, we saw 8.1 was at minus 2. That was 8.1. And then up here, 15 was at 1. So what you want to do is you want to count up all those percentages in there. Okay, so if you go back, I'll go grab it. Okay, so here's where I did it before. So here we said we had between 2 and 1, and we added up all those percentages in between there. So when you saw that, you added it up, it ended up being 81.5%. So when you have, they're not the exact same, so this one was minus 2, that one up, you just add in all those percentages that you are in between, and that will give you the answer. So, and then the last one, this is where it changes a little bit. They actually want the number of crickets, so not the percentage. The number of crickets expected to be shorter than 10.4 when there's 850. So they just told you how many there are in total. Now, if we look at 10.4, 10.4 is at -1 standard deviation. So they want, if we're at -1 standard deviation and they want anything that's shorter than that, so that would be that way. If we remember, what was this little pocket? It was 16%. So you want 16% of the 850. So you change that to a decimal and times 850. And what's our answer? So it ends up being 136 crickets are shorter than 10.4. Alright, so now we're going to look at a standard score or a Z-score, and all that is telling you how many standard deviations you are away from the mean, yeah? So if you think about it, I'll just give you an example. If you had a Z-score, if your Z-score was 2, then you are +2 standard deviations above the mean. So does that make sense? So before, when we said 12.7 was the mean, and then you added 2.3, you are sitting, if you've got a Z-score of 2, then your 2 standard deviations added onto the mean. Okay, so that's what a Z-score is. Sometimes they call it a standardized score, or sometimes they say Z-score. So how do you calculate the Z-score? So the Z-scores, when they take the data value. So sometimes I like to say you might say the actual score. So if you had a test, that would be what you got on the test, and then you minus the mean, and then you divide it by the standard deviation. Okay? And that would give you the Z-score for your effort on the test or whatever. Okay, so Z-scores, as we know, if it's telling you how many standard deviations you are away from the mean, we know, therefore, we could have positive and negative. Because if you have the mean, we know we can go -1 standard deviation. That would be a Z-score of -1. Yeah? If you go +2, that's what I was saying, you'd have a Z-score of +2. So we can have, if the Z-score is positive, you're above the mean. If you get a Z-score of 0, that means you're here. You haven't varied away from the mean. So if you get a Z-score of 0, you actually have the average. And if you get a negative Z-score, you are below. So sometimes we are given the Z-score. So here we know what the Z-score is, and we know the standard deviation, and we know the mean, and the question is to find the actual value. So this is really just a rearrangement of that formula, yeah? So where you would have the mean plus whatever the Z-score is times standard deviation, and that will give you what they actually got, okay? So it'll give you, they call it X up here, all right? So let's go. So here's an example of a student who got these, this is their scores they got for all their VCE subjects. So this is their actual mark. So this is actually what they got on the test, yeah? So in our formula, they called that X. Then we've got the class mean, or whatever, the data, or whoever they did. And we've also got the standard deviation here. So remembering that when we said the Z-score formula was the actual minus the mean divided by standard deviation. So if I'm going to go calculate the Z-score for his English subject, I'm going to go 69 minus 60, because that's his actual, divided by 4, and you'll end up with, he's got a Z-score of 2.25. Okay? So what do we mean by when we say their performance? So if you think about that bell shape, and we think about it here, here's his mean, and if he's at 2.5, if I have 1 standard deviation, 2 standard deviation, if they're at 2.25, they're somewhere here, aren't they? They're sitting up here. So what we like to say when we're talking about their performance, we just go to the nearest the one that they're above. So he's above 2. So we will say, because that little pocket is the 2.5%, we're going to say they're in the top 2.5% of the distribution or of the data. I'll just say the data. So it could be the group or whatever this was. Okay? So, and that's why we're saying that. So if I look at the next one, and I do find out his standard deviation, he had 75 was his actual, the mean was 60 in this case, and the standard deviation was 5. So he gets a Z-score of 3. So that's a very good score, isn't it? So they are in the top. What percent would we say for that? When we had 3, when we were plus 3, we would be way up here. So he's in the top 0.15%. Remember that little tiny little tail? There's very little amount of people better than this person in bio. Okay, so then if we keep going through them, then we got the chem one. Now, chem, he got 55 and the average was 55. So what was his Z-score? Yeah, good, 0. And so, we like to be a bit positive about the situation. So I'm just going to say they're in the top 50%. You could also say they're in the bottom 50%. Yeah, they're right on. Top 50% or 50% are above him or below him. So then we've got further. And then further was 55 minus 44 divided by 10. So it's got 1.1. So if we drew the thing, so he's higher than 1, so we'll just go with that pocket. So what was the pocket if you were just above 1, that higher pocket? How much percentage was that when we had 1? 16, excellent, that was right. 16, so we're going to say they're in the top 16% of data or whatever. And then the last one, we had 73 minus 82 over 4. So we see a negative 2.25. So if you drew that, they've gone below. So minus 1, minus 2. So we want this little below pocket, which was 2.5. So I'm going to say the bottom, they're in the bottom 2.5%. Does that make sense? Because they're just a little bit less than the 2, so we'll just say that chuck them in the bottom. So then what they'll say is they'll say rank this subject, because we can't rank just on their mark alone, because it's all different, and the score was different and the average and standard deviation. So that's why we do these Z-scores. So the higher the Z-score, the better the performance. So they definitely came first in biology. Would you agree? With a Z-score of 3. Then they were followed by, was it English? Second. Then they were followed by further maths. Yeah? And then then chem. And then the worst performance one was psych. 1. A student's mark on the class test is a Z-score of negative 2.1. So they are below the mean. On the basis of this scoring, assuming that the marks follow a normal distribution. So I told you they have to tell you that. And as soon as you see that, you're dealing with the bell shape. So if he's got a Z-score of negative 2, he's down here somewhere. They're sitting down here. Okay, so when they say it can be concluded that his test mark is in the bottom 2.5%, is that true? That is true, isn't it? Because that little pocket is 2.5, but not in the bottom 0.15. That's true too, because it hasn't gone to negative 3, has it? So this one is the good answer, I would say. Now, you've already found the answer in the question. It's question 1. So here's a hint in the exam. Question 1 will be that straightforward. So if you've got your answer, move on. If you get to the end of the exam and you've got time and you're checking, don't go and check that these ones are wrong. Yeah? So you go check that they're wrong. And that means you're checking something else, or you look to see, no, that can't be correct. Because when we check our work, if we check what we just did and the same way, we'll just do the same thing because we're justifying that we're right. So sometimes if you check the other answers, you'll go, oh my God, I get that right too. And that will make you have a good think about it, and you'll find the mistake that you've done, okay? All right, let's have a look at question 2. It said a student's standardized mark, so that's just another word for Z-score, was negative 1.7. The mean mark was 55 and standard deviation was 2.85. Their mark on the test, so that's what they want, the actual mark. What did actually happen? So if you remember back there before we had that formula, it's just a rearrangement of the Z-score, so you don't have to use it. You can just use that and do solve, but I'm going to do the actual, where it was the mean plus your Z-score times the standard deviation. So in this example, they told me what the mean was 55, plus their Z-score was negative 1.7 times 2.85, and what do we get? I think we get 51 or something, was it? 50.5 something. So what's it closest to? 50. Okay, the weights of players in a basketball competition are approximately normally distributed. So there they are, they told me that. And then they said with a mean weight of 78.6 and a standard deviation of 9.3. There are 456 males, so they told me how many in the competition. Now, the expected number, just be really careful. So we need an actual number of the male players in the competition with weights above 60. So they've given you a weight. So as I said, it's always probably going to have something to do. It'll be one of the numbers, perfectly. So we've got a mean of 78.6. 60 is below, so I'm going to go down. So minus 1 standard deviation. That would be 78.6 minus 9.3. What does that end up being? 69.3. And then if I go another minus 2 standard deviation, and here you go, surprise, surprise, we're on 60. So see how I said that it'll always be one of them. They make it nice for you. All right, so they want the expected number of players that are above 60. So if I'm at minus 2, how much percent is above it? This little pocket in here would be 2.5. So this will be, so if you minus that, good. This one would be, so you want 97.5% of the 456. So you change that to a decimal and times it like that. And what do we end up with? I think it's 445 is the answer. Brett and Sanjeeva both play in this basketball competition. So this is from the question before. So what did they say the mean was? Because I need that information. What was it? 78.6. And this was 9.3, I think. Okay. So Brett and Sanjeeva both play in this basketball competition. When the weights of all the players in the competition are considered, Brett has a standard weight of negative 0.96 and Sanjeeva has a standard weight of negative 0.26. So what you could do is, and now they're saying which of the following statements is not true. So with these, I like for myself, like to have a visual. So I'm going to draw a visual. Okay, so the mean here is 78.6. Now, if Brett is at, if I go down minus 1 standard deviation, Brett will be, he's very close to that. Not quite there, but there's Brett. And if I look at Sanjeeva, they're just a little bit less, so there's Sanjeeva. So that's how the scale would look like. So this is their weights. So this is the maximum weight up here, and this is the minimum weight down here. So when we look through the questions, it says Brett and Sanjeeva are both below the mean weight of basketball. Is that true or not true? That's true. So that's not what we want because we're looking for the not true. Sanjeeva weighs more than Brett. Looking at my diagram, it's very easy to see that's true, isn't it? He's up here. His weight's here. Sanjeeva's here. Brett's lower. Okay, if Sanjeeva increases his weight by 2 kilograms, he would be above the mean weight for players in the basketball. So this is what we're trying to we need to find Sanjeeva's weight. So this is really saying like his actual. So we could use that formula before where we said the mean plus the z-score times the standard deviation. So we've got all that data because it said in this question, it said 4 and 5, you use all the same data. So we're going to go, all right, 78.6 plus now Sanjeeva's z-score was negative 0.26. Okay, so I end up finding out what Sanjeeva's actual weight was, which was 0.2. Now the question's saying in here, if we increase his weight by 2, so that means if I add 2, it would be above the mean. I would get 78.2. Is that above the mean? No. So this is not true. So I'm going with that answer. I'm going to move on, and if I come back later, I'm going to check these guys and make sure they're, incorrect for the question. So is Brett weighs more? So if you go and do the same formula for Brett, you'll see that he does weigh more than 68. And if you do more than 50% of the players in the competition weigh more than Sanjeeva, we can already see that because he's below the mean and 50% is above the mean. So that's definitely true. We can tell that already.